Welcome to the second week course of principles of vibration control. So, what are the things that we will look focus to in this week? We will focus on dynamic properties and selection of materials. Okay. So, we now know that what are the various parameters of a vibrating system. You are also familiar with different strategies of vibration control. So, the first important thing now is that if I have to design a structure which should be safe from vibration point of view, what are the dynamic properties that I need to check and how do I select materials for such structural design. In this week, we will focus on that very aspect. So, the first thing that we will see is that if the structure itself can dissipate the vibrational energy, that is the best thing, because then the vibration can get controlled very easily inside the structure itself. So, we will first see that how the energy dissipation can take place in the structural material itself. So, that is what we will first focus on. Now, towards this direction, I will talk about quite a few things. First of all, I will talk about how to select a structural material from the vibration control point of view, because when we generally choose a structural material for a mechanical design. So, let us say that this is a mechanical design we are looking for, then we generally choose it from say deflection point of view, where the stiffness becomes important. In other words, this also means that we actually check properties like modulus of elasticity, and there is another mechanical design which is actually strength based design. So, where things like ultimate tensile strength, this becomes important for us, ultimate tensile strength, shear strength, etc. Okay, parameters like SSU, that becomes important for us, but we rarely, in fact that is very important, that we apply regularly structural materials for vibration control point of view, but we rarely keep that from the vibration control point of view what parameters are important. Is this modulus of elasticity important, or SSU, or anything else that is important. So, that is what we are going to look into today, and we will also see that this energy dissipation, what is the stress dependence of this energy dissipation, we will see it. There is something called a material loss factor, I will introduce it today. You can even get it for composite materials. So, that also we will see how to get it as a special class of material loss factor, and then we will talk about how we can model linear hysteretic damping. So, these are the things that we plan to do in this particular lecture. Okay. Now, the selection of the structural material corresponding to high inherent energy dissipation capability, they actually further depend on three factors. One factor is called the material property of the structure. So, that is what we will be, I have just touched on that. So, that we have to see. We will also see that the energy dissipation depends many times on the geometric property of the structural member, and it will also depend on the type of loading, like whether the structure is undergoing bending, torsion, or combined bending and torsion, or axial loading, etc. So, in addition to material properties, geometric property and type of loading also come into picture at times in this case. Now, the material properties, first of all, if we look into it, because selection of materials, that is the primary important thing for us, then in the material property, the first important thing for dynamic application is actually the inertia, which in an indirect way will depend on the density, and cross section of course is not a material property, but density is a material property. Similarly, when we talk about stiffness, This is governed generally by Young's modulus, shear modulus. In some cases it will be in addition to that there can be Poisson's ratio. There are some negative Poisson's ratio material which we will call auxetic materials, which has the Poisson's ratio variability also come into picture. And the stiffness, of course, it does not only depend on Young's modulus or shear modulus, but also depends on geometry and the mode of loading. For example, you consider a very simple case that you have a kind of a cantilever beam which is subjected to axial loading P. So, if this is of length L, then we know that the deflection corresponding to this force P, the deflection delta that would happen into it due to this tensile loading, this structure is going to deflect, and that is the modified these things, and delta is the deflection, and that equals to P L over A E, where A is the cross sectional area of the system. So, A is the cross sectional area and E is the Young's modulus of the system. So, that is what is the deflection for the system. So, we can see from here that the stiffness, if we define, that is the P over delta, K is P over delta, and that is actually A E over L. So, that means the stiffness not only depends on the modulus of elasticity, but also depends on geometric properties like length, area of cross section, and also the loading, because corresponding to this axial loading it is P L over A E, and if I consider some other loading, let us say we have something like a bending loading, etc. So, then this expression is going to get changed, right. So, if we consider the bending deflection, then this will be a different deflection variation with respect to the loading condition and all these things. So, these two will differ. So, thus the stiffness itself would vary depending on not only the material parameters, but also on geometry and the loading condition. Now, all this is fine, that is as far as the inertia and stiffness is considered, but also the damping is going to change, and that also we need to look into it. Often we totally neglect this part of the parameter, and that is what we will actually bring today into picture. So, when we have to think of the damping capacity of a structural material, then what is there in the material inherent property that actually gives this nature of damping, that we have to think of it. Okay. So, there can be many mechanisms inside the material. For example, there can be dislocation movement, which generally occurs due to the presence of slip planes in the crystalline materials. So, you know that in any crystalline material there are certain planes inside the material which are actually prone for slipping, because they are so high density that the layer can actually give away if there is a shear force. So, this slip plane shifts and it goes towards the grain boundary. This is what we call the dislocation movement. Now, during the vibration, this energy can be supplied such that this slip plane movement occurs and it goes towards the boundary, the grain boundary, and hence this process will consume some amount of energy in the terms of dislocation movement, and effectively that will be reflected in terms of increase in damping of the system. So, thus dislocation movement contributes to damping. Similarly, there can be grain boundary slip. So, if you consider a small structural material, and if you look at it, let us say using a microscope, okay, with a 100x kind of magnification, and if it is a metal, for example, okay, what you will see is that there are various such grains, and the grains are actually the crystal structures which has one single direction of orientation, maybe one in this way, another in this way, etc. So, these are directions of crystal orientation. Now, in the first case, the dislocation movement, if there is any failure inside this grain, then during the movement it goes to the boundary. That is what is our dislocation movement. The second case, the grain boundary slip, the grains themselves, particularly wherever there is high angle of attack. Let us say this grain has a crystal axis in this manner, and this grain has a crystal axis in a the relative angle is very high between the two. So, then there will be a continuous slip between the grain boundary, and that will also consume lot of energy, and hence the energy dissipation will increase. Also, there can be magnetoelastic effect. This I will explain much in a much better manner later on, but right now we can think of it that the magnetization and strain actually are coupled in a magnetic material. This was shown by Joule long before, that in a magnetic material, if it is depending on the grain structure, the grain boundaries etc., the magnetization actually changes. So, if some part of the mechanical strain is converted in terms of magnetization, then that will also dissipate energy, which is what is our magnetoelastic effect. Similarly, you know about phase transformation and other expansions, anomaly expansions. So, that gives rise to the thermoelastic effect of the system. And finally, there can be some localized plastic strains for some presence of defects like shear bands, which can entangle the dislocations, preventing the crystal from sliding, or maybe that if you consider a particular grain and then inside the grain, suppose you have the dislocation here, and then you have some pinning by the interstitial position. So, these are the pinning of the pinning, you call it the interstitial atoms. So, if that comes into picture, so there will be some localized plastic strain that will happen, and that will also contribute to the damping of the system. Thus, there are the several kind of mechanisms. Each may happen that only one of them responsible. It may happen that there are many competing mechanisms happening inside the structure, which will all contribute to the structural damping of the system. Now, be whatever is happening inside, if I take a structural material and let us say I subject it to harmonic loading, and then I look into the stress strain plot, particularly at a low stress level, then what I will see is that the stress strain diagram actually goes somewhat like this. It starts from here, and with the reversal of stress, the strain comes out, but there is some plastic strain here. You reverse it further, then it goes the other side, and then it is continuing, and this cycle continues on and on. So, that is how you get this, and this area under it is actually the energy that is dissipated due to hysteresis, we call it. The reason for hysteresis could be all of those kind of internal dissipation that is taking inside the system. Now, suppose we define this energy which is dissipated per unit volume of a structural material per unit cycle by dm, which is actually given by the area of the hysteresis loop. Then this is also the mechanical hysteresis loop. Then this dm, this has been found out experimentally mostly, that this dm actually varies with the applied stress sigma in a manner that dm equals to j times sigma to the power n, where the j is known as the damping coefficient and n is known as the damping index. Usually it varies from 2 to 3 in the working stress range. So, if n equals to 2, generally for very low stress regime n equals to 2. So, that means the energy dissipation is varying with the square of the stress it is subjected to, and if it is at a higher stress range, it may vary with the cube of the stress. Actually, there is another competing theory which says that you can in fact express this dm as j epsilon to the power n bar instead of sigma to the power n. So, this is a strain dependent coupling, and you may put a different constant here. So, this is a better way, is because here this j is not actually stress dependent, like in this case there is a unit dependency that will come here, but in this case it is not there, but somehow this particular form is more accepted due to historical reasons, and we will continue with this particular description. So, at very low stress level, if I carry out, so that means suppose I take a structural material and with respect to time I am applying a stress sigma. Now, suppose this sigma is a alternating stress, right, that is what is giving us the hysteresis. If that amplitude of stress is quite low, then we are going to see that this is what will be the energy dissipation per cycle. Okay. Whereas, if we increase this amplitude to a higher one, of course, it should not fail, then you would see this particular thing, that means this elliptic shape will go out, it will vanish and it will become more like a pointed shape at the two ends, and that is what happens as the stress amplitude increases. And also the expression then becomes, instead of sigma to the power sigma square, it would become sigma cube. Now, one important thing, however, in this discussion is that dm is independent of frequency. So, hysteresis loop does not alter with respect to frequency. This is a very important property of structural damping. Why I am telling is that in case of a viscoelastic material or a damping a rubber damping etc., the excitation frequency matters a lot. So, suppose this stress level in this case, even if it is a relatively high frequency or if it is a relatively low frequency, in all the cases this energy dissipation there will be no change, as long as the amplitude remains constant, there will be no change. Whereas, for viscoelastic material there will be a tremendous change between this and this low frequency and high frequency. And I told you earlier that for viscoelastic material, if the frequency changes, let us say omega, and then you would see that the modulus of elasticity, for example, changes very much, and low frequency, remember, is always like a high temperature situation, and high frequency always behave like a low temperature situation. So, that is the way it is going to behave, and since the modulus of elasticity is changing, so corresponding to that everything will be changing. Now, if you compare the performance between a viscous damping and this damping, then energy dissipated per cycle here is proportional to the square of the amplitude. So, in viscous damping, energy dissipation increases linearly with frequency. So, it is frequency dependent, it is actually pi c omega x square, and in this case it is not frequency dependent, it only is proportional to the square of the amplitude. So, that is the difference between the two system, and over that you can actually find out an equivalent viscous damping expression. So, keep in mind that for viscous damping it is pi c omega x square, where that means it is dependent on the square of the amplitude, it is dependent on the frequency, it is dependent on the damping constant. Whereas, for this type of structural damping material, you would see that it is not the same. Here the d, I will come to it how we can get the equivalent damping, but before that, if the n is greater than 2, then for the stress dependence there are some other representation also, which is for the sake of completion we should keep in our mind, that you can actually represent it by using two damping constants. One is J1 sigma square and another is J2 sigma to the power n. So, basically one is related to the elliptical area of energy dissipation, and the rest part the text is taken care of by that J2 sigma to the power n. Now, if the stress becomes multi-axial, because there are many cases where the stress may not remain actually uniaxial. In such a case, if the stress becomes multi-axial, then this sigma is to be actually replaced by sigma equivalent square. Otherwise, if you look at it, that our expression is same, it is again j sigma equivalent to the power n. So, only thing we are now writing it as equal to j sigma equivalent square to the power n by 2. So, basically it is j sigma equivalent to the power n, and where the sigma equivalent square is actually that depends on the stress constants lambda 1, the Lami's constants, and also the stress invariants I 1 and I 2. So, these are the three parameters which actually if you know, you will be able to find out the equivalent stress in case of a multi-axial loading, where your I 1 as the stress invariant, this is sigma 1 plus sigma 2 plus sigma 3, and I 2 is sigma 1 sigma 2 sigma 2 sigma 3 and sigma 3 sigma 1, where sigma 1 sigma 2 and sigma 3 are the principal stress amplitudes. So, for multi-axial case we can handle the situation by knowing all these principal stress amplitudes, then finding out I 1 and I 2, and also we know this Lami's constant lambda 1, and its value is usually between 0 to 1 in this case, and then we should be able to find out the sigma equivalent square. Now, the material loss factor could be expressed as eta m, that is the material loss factor, as the energy dissipated per cycle, that is d m, divided by the 2 pi W m, where W m is the maximum elastic energy per unit volume in the cycle. For a very simple case where it is there is only uniaxial loading, you know that W m is actually the area under the stress strain curve, which is sigma square by 2 E, and that itself becomes slightly more complicated for multi-axial loading, and it becomes here as I 1 square by 2 E minus I 2 into 1 plus mu over E, where mu is the Poisson's ratio, E is the Young's modulus. I 1 and I 2 we have already defined here. So, you should be able to find out that what is the W m, and d m you can calculate corresponding to this particular formula. So, we should be able to find out the material loss factor for any particular case if we know these stress invariants and the other mechanical properties of the system. Now, so we can calculate the W m and d m, and we can actually get the material loss factor. Now, if the sample happens to be a composite specimen, okay, so composites are generally, I will come into that discussion at a later stage, but they are generally layered structures, and they are also used very much for many such vibration controlled systems, because they have excellent internal damping properties. So, this is, suppose this is like a composite beam, and this actually would look very much like your sliced bread. So, this slicing can be in different manner, you can depending on the situations, but it can be either like this is one way, or it can be something, if you look at it, that it can be in some other manner. That means, for example, it can be in this manner also. So, if you have thus various types of these layers, then you have to calculate this for each of the layers. So, as a result, as you can see here, that suppose it has these n layers, then you have to calculate the energy that is getting dissipated in each of the layer by this expression, and then integrating it over the whole length. So, first you calculate along these layers and then integrate it from this to this, the whole length, and similarly you can actually find out that how much of energy is stored, and that also you can do over the whole length. So, basically that is the way in which we do it for a composite specimen. As far as the materials are concerned, the kind of isotropic materials like say aluminum or steel, etc., for them the order of loss factor I already discussed earlier, that aluminum is possibly the lowest, and concrete or cast iron, they are possibly the highest in terms of the order of the loss factor. So, that is how we can actually calculate the loss factor and compare it with the loss factor of some of the very important materials. Now, let us come to a situation where we would like to find out that for a linear hysteretic material, what are the selection criteria for the system. In order to do that, what we have done is that this is an equivalent Kelvin Voigt representation. Why equivalent? It is because simply that damping part, equivalent damping of a KV model, the damping part we have actually replaced by a C equivalent here. Now, how do I know this C equivalent? Well, for the first point is that the energy dissipated per cycle, we know that it is proportional to the square of the amplitude. So, which means if you use alpha as a constant, you can write D equals to alpha mod of x square. Now, compare that with the energy dissipation had it been a viscous damping, and you know that for a viscous dashpot it takes the expression of pi c omega x square. In this case, only thing is the C is C equivalent, because we are actually trying to find out what is the equivalent viscous damping constant that can actually replace this. So, we can put C equivalent here, and since the x square is going to get cancelled in both the sides, you will get C equivalent as alpha over pi omega, and this alpha over pi is actually denoted as the hysteretic damping coefficient H. So, that is how we come here as the equivalent damping constant, which is actually H over omega, where H is the hysteretic damping coefficient. Now, with this you can also calculate the loss factor. Remember that the loss factor expression has energy dissipation, which you can write as alpha x square, is proportional to square of the amplitude, as we said earlier, and the work done is actually 2 pi times half k x square, that is the energy that is stored in the system. So, basically you are going to get it as alpha by pi k, and since alpha by pi is H, your hysteretic damping coefficient. So, you can write this as H over k. That means the loss factor depends on the hysteretic damping coefficient H in this case, and also on the stiffness of the material. Now, let us look into the equation of motion of the system with this change. So, we know that in case of a I have earlier shown you that in case of a conventional damping system, the equation of motion is mx double dot plus cx dot plus kx equals to f e raised to the power j omega t. This simply comes if you consider the equilibrium of this mass m, this is your mass m, and then this is subjected to f e raised to the power j omega t harmonic excitation, and because of that there is a inertia force mx double dot, and there is kx and there is cx dot. So, basically all these things together, if I make the equilibrium equation, I am going to get this particular equation, where the only thing that I have done is that this C, now I have replaced it here by H over omega by using the equivalent damping concept. Now, here if we are only interested on the steady state solution, then I can substitute this x as capital X e raised to the power j omega t, and then this capital X will become f by k over, if you just do this algebra thing. So, we can just try it for this particular case. For example, if I just write it somewhere here for your ready reference. So, we have done it earlier also, that means it will become minus omega square m x e raised to the power j omega t will get cancelled from both the sides, plus h by omega, and this is again j omega x plus k x, which will be f itself, and then if I take all of these things together, I can write it as k minus omega square m plus j h over the omega gets cancelled. So, plus j h times x equals to f, and then if I take the k, if I divide it by the k all along, then this would become 1 minus omega square m by k plus j h by k, okay, and that times x will be f over k if I divide everywhere by k. And then I can get this expression, because just a simple algebraic extension will give you this particular expression, where x is f by k over 1 minus m omega square by k plus j h by k. And I can now also write this h by k as the material loss factor j eta. So, the amplitude of x will be what? The amplitude of x will be amplitude of the numerator, that is amplitude of force over k, and denominator what we are going to get is amplitude of 1 minus m omega square by k square. So, it has to be 1 minus omega square plus eta square, and the whole thing will have a square root. This omega of course is omega over omega n. So, a little bit of simplification will give you this non-dimensional excitation parameter. So, this is what will be our amplitude of the displacement for the system. So, thus we can get an expression for the whole system, and in the next lecture I am going to talk about the selection criteria now corresponding to this linear hysteretic material. So, we will discuss this with respect to a numerical problem. Also, we will talk about how to design this for enhanced material damping. Thank you.